I assume most of us are familiar with the supernova problem, right? Some supernova simulations result in explosions, some don't. We've learned a lot over the past decades of studying this. I see a lot of analogies between that problem and the problem of binary neutron stars. There's just so much physics that we have yet to incorporate into these simulations. I think the future, regardless, is a bright one. We have a lot of very talented folks, myself excluded, talking about developing some very neat techniques, I think, in this regard. And I'm excited to see where this field is in 5 years. We need a lot of effort, basically 10 years ago, to be ready for what LIGO is producing now as we speak. But you know, we can only do with what the codes and what the CPUs we have in our. Well, we can only go to war with the weapons we have, as they say, right? So we're doing the best with what we can, I think. I think an enormous injection resource, a Manhattan Project, if you will, of worth of effort could really boost this field and maximize the science output from LIGO in the near future. And who knows what's coming next.
Okay. So I think I'll pass it around.
Okay. I think there are many outstanding problems connected with binary neutron-star mergers. Among these is trying to understand how the systems evolve over longer time scales than just 2 milliseconds after merger. I think we're starting to have a good understanding of when, for example, front black hole formation occurs for which binaries. But we don't know, for example, in the case in which we form hypermassive neutrons, how long they're going to survive. We don't know exactly how to connect the outcome of the merger with possible observations beyond gravitational models. And also, we cannot currently model the gravitational wave emission in the post-merger with the same accuracy as we can in the inspired. So there is a lot of work to be done in this direction. So I think one important aspect is understanding the nucleosynthesis yield from neutron-star mergers. This is something we have not discussed in detail, but what current simulations show is that the electron fraction of the material is very close to the 0.25 critical limit between forming and not forming elements like gold. So in order to really have quantitative models, we'll have to work very hard, because this is a problem where the output or the outcome is sensitive to neutrino-matter interactions, and where things are very close to this critical threshold where small change can push them one way or the other. So we need to work hard on this. And the other issue that I think we need to address somehow is understanding the role of the small-scale magnetohydrodynamic turbulence in mergers, and at least how we can quantify our uncertainty due to these small scale effects.
Okay, so I sure agree with all this. I would take a more general point of view, more astrophysical if you want. We had this great breakthrough of binary merger with electromagnetic amplifiers, and this was a triumph of the theory, and the two major chapters of this were the shock reverse, that in the end turned out to be, after a whole year of afterglow observation and so on, a canonical shock reverse like the others we know, much farther away, but still not axis. So this is open a new way of studying this. And the other thing was the kilonode that was predicted, and was remarkably similar for the first case that we really could characterize at photometric and spectral level, remarkably similar to the expectations. So really trying for the theory. But from this observation, we couldn't really graph the properties of the underlying system. We still have this big question of what was the remnant coming out of the merger. And besides, gravitational waves is a very important part. If we look at these two big elements of the multi-messenger of the electromagnetic side, I think one should, if one wants to really understand binary merger making theory, one should take into account the gap that we have between the scales that we cover with binary merger simulations, time scales, spatial scales, with the scales that are relevant for the production of these electromagnetic counterclocks. So for a jet production is a multi-scale process and will go on a much longer time scale. And spatial scale that we can cover with is binary star merger simulations, and the kilonov as well is something that then the actual signal emerges on much longer time scale. So one point I would stress is, like, one possible direction is something that people are trying to do is to try to fill this gap. For example, in the TCAM project that being discussed here, trying to pass data from binary star merger to other type of codes that can go on these much larger scales and fill the gap between what we have in a merger simulation and what we need for electromagnetic counterclock production.
As I sat here thinking about what I wanted to point out, I found myself concentrating on an art what became a sort of linear combination of what first studied and then Ricardo said. And so I'll just gloss a little bit, amplifying their remarks from a slightly different point of view, which is that in the discussions today, there was in large part an aversion of glance from some of the more important issues having to do with the electromagnetic side of the events. One of them is very much the progress of nucleosynthesis in the orbiting material, which depends on neutrino irradiation and neutrino transfer, and in a number of respects is an element that will likely need improvement in the calculations. Another is the separation in timescales, which you mentioned. And after all, the gravitational wave signal is a matter of milliseconds to tenths of milliseconds. The gamma ray burst, which in the case of 170817 was actually the way that we were alerted to what was going on. That's a matter of seconds. The quote kilonova was sort of hours to a couple of days. And then there was continued X-ray emission over months. So there are very disparate timescales, and they almost certainly will require different methods and somewhat different physics. Some of these interact. How much matter is left behind and in what physical state determines both the nucleosynthesis, it's a kilonova result. It's also jets through the issue of the overburden, which I mentioned earlier this morning, of can any jet driven by a resulting black hole punch its way through the surrounding material, and what are the circumstances? To close the loop on the jet will also require additional physics, which is unfortunately even more poorly known than some of the nuclear physics of nucleosynthesis, namely the acceleration of electrons, relativistic energies, to produce the gamma rays, etc., of a gamma ray burst. That's another story. Other groups, other communities are working on it. So it's going to be, so then cycling back to the overview, here are all these disparate outcomes requiring various kinds of physics and various scales. But this is presumably a causal system. If we could specify the masses of the neutron stars going in and their initial magnetic fields, and the character of the initial orbit, then presumably we ought to be able to predict these things. And that's a tall order, but that naturally is the goal.
Okay, so I would like, yes, now I would like to ask the audience to comment and to engage in discussion based on the points that are made, or if you want to make additional points. So Thomas.
So basically just along the lines of Julian ended with that, I'll call it a thought. I'm not sure whether this qualifies as a question or comment, but basically, it's my understanding that instead of evolution, it is actually quite difficult to create a map between initial, let's say, main sequence masses and final outcome, say, of supernova. And the problem is that the evolution starts going through phases that were different processes starts on the scale. There's convectional, mass loss, things that are very difficult to predict. And actually, in some sense, almost stochastic. Use different codes, compile with different compiler, they make it different results. Because time errors, truncation errors will achieve each different outcomes. So it's almost like a chaotic game error. And therefore, it's actually very difficult to make a clear link between, let's say, main sequence masses and the outcome of supernova, like whole or neutron star. And in fact, basically, not those masses, they're islands and it's very complicated. And that made me wonder whether do we really have the confidence of what you just said? Maybe should there be a unique map between basically initial ones and neutron stars and the outcome? Because in some ways there's something similar going on here, what we heard about this morning, about the instabilities that here, the interface between the two stars match. Basically, those instabilities could go to very different magnetic fields, just depending on how the stars are rotating, how the magnetic fields are aligned, what the initial strength is. So you could actually get very different outcomes. And as I said, this is a question rather than a statement, but basically, do we really have the confidence that we can map, like as you said, initial masses, spins, orbits, to a unique outcome? Is that entirely clear?
So if anyone want to take this question, I believe Philip had some slides that might actually respond to some of the questions you asked. I don't know if he's connected.
Slides? Slide?
No. Philip Meshta, is he in the virtual audience?
Yeah, Philip is on.
Okay. So whenever he wants to speak, please raise his hand. Yeah, picture.
Okay, maybe I can comment on this.
Yeah.
It's true that it will be challenging to map what LIGO gives us into, for example, the electromagnetic counterpart. However, I'm not sure that the system is as chaotic as stellar evolution. For example, we know that we can rule out, for example, the case in which a black hole was formed immediately at the time of the merger. And there are very well-defined universal relations that are EOS insensitive that tell us, for example, when a black hole forms immediately at the time of the merger. In all of these cases, what we find is that there is no mass or no material left outside the event horizon, so we can rule them out as being the possible source for the kilonova we have seen. In general, what we find is that there are some quantities, in particular the amount of material left outside of the event horizon, that depend strongly and in a rather smooth way on the equation of state. So as we make the equation of state stiffer, we increase the amount of mass in these pieces. And supposedly we also increase the amount of material available for nucleosynthesis and to produce the kilonova. And this mapping, as far as we understand it now, seems to be rather robust. There are changes by the accretion of this mass can vary by a couple of orders of magnitude. So it's not something as subtle as a corporal supernova where you have explosion or explosion depending on whether you are rightly above some critical threshold or slightly below. So I still have hope that the system is rather robust and that the outcome does not depend sensitively on very small scale effects.
Maybe just to increase the hope, the fact that we have multi-messenger investigation is a great advantage. So we can compare predictions with different channels. Even a number, just from the electromagnetic side, we have a number of different electromagnetic counterparts, each of which can help constrain some of the aspects. So there will be aspects that are a bit critical, like predicting from given initial data. You were mentioning that the lifetime of a hypermassive neutron star in this very delicate phase. So in that case, we would have to go the other way. There are multi-messenger analysis ways of constraining how long the thing will survive, and then we have to deal with the fact that there is a range of models that are compatible with that lifetime, because this is somewhat delicate. So there are aspects like that. But overall, I think we have many different ways that we can take different paths, and a combination of those that gives me hope that we can understand most of this.
Yeah, if we can add one thing about the outcome of learning from star mergers, it's true that if we have a hypermassive neutron star, we cannot really reliably tell from simulations how long it's going to survive. But we are fairly sure that it's not going to survive for extremely long time scales, because we know that these objects are unstable once they reach uniform rotation. So from this point of view, the problem is different from core class supernovae in the sense that there are different qualitative outcomes: supermassive, hypermassive, massive, from black hole formation. And I don't think that there is a way to really jump between these different outcomes.
Okay.
Philip is online and he has some comment. Sorry.
Okay. Go on, Philip.
Can you hear me?
Yes.
Can you mute that? Can you mute that so the microphone?
Sensitive to its small scale features as the supernova problem is. But I think still looking at the supernova problem, we can, as a community, think about how we want to tackle all the different aspects of this problem. Do we want to go about in like small groups here and there that work on individual things, or do we want to have a slightly more collaborative approach to what has been happening in the supernova field over the last couple of decades, where it was more competition driven? So I think there can be like advantages to both, but I think that's something where, as a community, how do we want to handle all this? That's a lesson we can look at and figure out if we want to do something differently, I think.
Yeah, so this is going back to the concept started by Zach. We need a Manhattan Project kind of thing to resolve this. The other option is to continue on the path we are in, obviously, and hope that single groups are going to make major advances and then learn from each other and move forward this way. I think both ways could work. It's not necessarily one way.
We're not broadcasting at the moment.
Oh, it's okay. I will just keep going and you broadcast. I don't know what. I think that both ways are possible, or maybe a combination of both actually could be possible. But it's true that we are under-resourced, and so if we decide to move in parallel to reinvent the wheel, that's going to slow us down. If there is a way for us to share enough of the pieces, let's say, that are critical to all these efforts, and being able to share those pieces in an effective way, then maybe progress is going to be faster and we are not going to have to reinvent the wheel. This is a question that I think is going to be taken actually to the next panel, panel 1, that is going to address the role of the Einstein Toolkit, because many of the codes that we are using here, maybe with the exceptions of Spectre and Danger, many of the codes here have somehow inherited through the course of the history something from what today we call the Einstein Toolkit or the Calculus community. So I think it would be beneficial to see how we can move forward in providing those pieces that are needed for this group to be successful in what they want to do in terms of the physics, that is the driver, but not having to reinvent the wheel to re-implement necessarily the tools.
So could I just quickly,
Yeah.
could I just quickly comment on Thomas's thought? right? So I'm actually pretty actively involved in solving that inverse problem within LIGO. It's called parameter estimation, right? So we get a gravitational waveform from a binary neutron star, a black hole binary, and then it's our job to use an approximant that's trained on numerical relativity, basically to solve that inverse problem. Well, when we talk about binary neutron stars with an infinite dimensional parameter space, things suddenly become far more challenging. And I think if you look at observations of short gamma ray bursts, the rule of thumb is you see one short gamma ray burst, you see one short gamma ray burst. It's a very rich problem, and I think it's going to require orders of magnitude more effort than what the black hole binary problem has managed to, what we've done for the binary black hole problem in numerical relativity, to get a firm grasp on just some of the coarse-grained features regarding solving this inverse problem. That's my thought. I mean, I think these amazing efforts undertaken by, for example, Davide regarding many equations of state, many sorts of sets of initial data. We've got to do that, but we've got to do that times. That's like one dimension. I mean, it's not one dimension, it's multiple dimensions, but we need to explore more dimensions. And we need to add more physics, obviously. So it's insanely more difficult. And so it is a very valid thought that maybe it's not even possible. I don't want to think that. I don't want to throw that out there as a statement I'm confident in. I know it's very difficult, but I don't think it's impossible.
And I think there's actually a useful distinction to be made, which is that it is possible that some of the phenomena we're talking about truly are chaotic. It's also possible that some of them are going to be very, very difficult to work through in a quantitative way, just because they're so incredibly messy. I have in mind here, for example, actually predicting the UV optical infrared spectrum of the kilonova, because the spectroscopy of these lanthanide and actinide elements with vacancies in the F shells is extremely messy. It's going to get that into quantitative shape is something I don't know who has the intestinal fortitude to succeed with. So there may be limits. The useful thing is to distinguish those parts of the puzzle where we really can make definite statements from those parts where it's either in principle difficult or just practically difficult, and then to be able to say, make sort of overall character statements about the hard parts. I think that, for example, would apply to the gamma ray bursts, where indeed the detailed time dependence is like looking at fingerprints. And they're all a little different, one or another. But there definitely are shared common properties, as in, again, the Fourier power spectrum of ridges in your fingertips, not all that different from person to person. We can make, I hope, similarly big picture statements about those phenomena.
I agree, and I was going to say actually that same thing, that finding out what are the right observables to compare to or to try to explain is the first half of the job.
Maybe in the audience will be calculating observable and comment something? Looking that way, Jordan. He's trying to hide.
I mean, the problem with the inverse problem is, it's the same that we see the problem, for example, going from real transport to something like an M1 closure scheme. You're throwing out so much of the information to get something that's useful, that similarly when you get the observable and you try to back it up into all of the information that produced that, it's very hard still. We're still just getting first little snippets of information. I think the exciting, but anyone who's ever drawn any picture of a black hole with any underlying model appreciates that they all look like that, right? And it's going to be a while before we're both getting it right going forward and getting something useful enough at the end to go backwards. That was helpful, but
Well, very
or a wake-up
realistic.
call.
Very realistic. Okay, so any last comment from this panel? Any last comment from the audience before we proceed with the second panel? I hope the students and that have remained till this, the end of the meeting have any questions, or you're intimidated by the fact that this is a very challenging problem, but we really need you because I think because it's a very challenging problem, it's going to take probably more than a decade to get solved. So we really need you. Yes.
All right. Thank you for all the information. It's really useful. I had a question about the observational side. What do you think is the next big project to improve all of our knowledge of the electromagnetic counterpart of this phenomena? Do you think the level of simulations now compares to the level of observational information that we have, or some of them are ahead of the other?
Can I comment first? I think on the observational side, what we really need is observations in the first few hours after merger, because one of the big surprises of GW17 and 17 was that there was a blue kilonova that we observed after 12 hours. And it's not clear how this blue kilonova was originated. So understanding how this was originated will most likely require us to understand how the emission came out in the first place. So seeing the kilonova actually peak will give us a lot of information about the structure of the outflow. And the other comment I want to make is that if you look at just the kilonova light curve, there are many models in the market that do more or less equally well at picking the kilonova data, and they give completely different predictions for example, for the amount of gold. There are models out there that can fit everything and have no gold. So the goal of simulations is not really to have a model where I can press a button and I get perfectly the light curve out from the beginning to the end. But really what we need to do and where we can make a lot of progress is setting the boundary conditions for this modeling of the kilonova, for example. So the message is we don't need to understand everything in order to make important statements. We can already make some important statements today, but we have to understand the limitations of our methods.
And that's a very good point, which I think is sufficient to basically end this discussion on binary star, unless there is any equally very insightful comment in that direction. All right, so let's thank our panelists. And so the next panel is going to be in the Einstein Toolkit and the future of the Einstein Toolkit. I would like to ask people involved here in this. This is because it's the one is been changed because people have to leave. They have to take flights. Okay. All right. So Josh, you are on this one. Okay. Anyone else is an Einstein Toolkit developer here? Who's that? Oh, Bruno. No, Bruno is in the other one, but you can sit here if you want to. Are you in the Einstein Toolkit?
Wait, you finished it?
Come on, it's the same. You can stay on the other one too then.
Okay.
That's fine. There is a free chair. It's a free parking. Okay. So this panel has been tasked now to discuss what could be in the foreseeable future the path forward for the Einstein Toolkit. We already heard some voices from the audience, from the developers, from the GRMHD community, and I would like to take it from there, and whether it is realistic to move forward towards satisfying the needs of all these communities, and still while keeping pretty much the Einstein Toolkit alive and breathing. Yes? And who wants to start? Start from here? Okay.
So, sustainability and the Einstein Toolkit. So, I think that we have, it's very clear when you look at the Einstein Toolkit mailing list, when you look at